Okay, so in this second part of the video, we'll just go over an example to see how we can interpret the coefficients in a logistic regression equation. So we're going to look at this example. So this is the example that you'll see in the tutorial. It's from the Titanic ship. So we're going to look at just keep things simple a little bit. So the response variable will be whether the passenger survived or not, and so the response is coded as 1 for survived, 0 for not surviving. And we'll just take a look at just one predictor variable, the amount of fare paid, and apparently that value has been adjusted for inflation, right? So let's fit the model, right? So that's the intercept of our logistic regression, and that's the slope of our logistic regression, right? So if one was to write this out, right, we are saying that the log odds, log of pi over 1 minus pi, and I put a hat over there to represent that it's the predicted probability, right? Then the intercept negative 0.293, I'm just rounding it off to 2 decimal points, right? Plus 0.01613 times the fare paid, right? So this is the logistic regression equation, and you want to convert this, right, into pi hat. That's totally fine. Predictor is significant, right? So it's telling us that this is significantly different from 0, right? Which tells us that since this is a positive slope, right, that means the higher the fare you pay, the higher your odds of survival. Maybe a little bit diabolical to think about that, but that's basically what the data are telling us. Now, if you want to interpret the coefficient, right, the slope was beta 1 hat was 0.01613. Right, so so this tells us the difference in the predicted log odds. So if you, for 1 unit increase in the paid fare, the predicted log odds of a passenger surviving increases by 0.016, the value of the slope, right, for a 1 unit increase in paid fare. So this is in terms of log odds. If you like to think in terms of odds, right, the predicted odds of surviving is multiplied by exponent of beta 1 hat. And if you work this value out, this is equal to 1.016. Right, for a 1 unit increase. That means the all odds will get multiplied. Your odds will be multiplied by about 1.6%. Right, so your odds of survival increases by a factor of 1.016. Right, for a 1 unit increase in the paid fare. Another way of stating it, right, the odds ratio of a passenger surviving for a 1 unit increase in paid fare, the odds ratio is 1.016. Right, so that's how we can interpret it. Right, so it's about 1.6% increase in the survival rate. So far, right, we talked about what happens if it's a coefficient for a quantitative variable. If your predictor is an indicator variable, it's categorical. The interpretation is a little bit easier, right? So again, let's assume we have a binary variable, right, coded 1 for males, 0 for females, and we are predicting if the person survives the Titanic, and we'll consider just a simple model again with just the gender variable, right? So we're going to say I1, right, where I1 equals to 1 if the person is male and 0 if the person is female. So how we interpret the coefficient is a little bit different with a categorical predictor, right? The difference in log odds of survival between males and females is the value of the slope. The odds of survival for males is this times, right? So again, the odds is multiplied by that factor. So the survival, right, because males is coded as 1, that means that whatever the odds are for female, right, so the odds for female, right, you have to multiply that by exp of beta 1 to get the odds for male, right? And the reason why is this direction is because male is coded as 1 and female 0. So if it was coded the other way around, then right, it's odds of male times exp of beta 1 gives you odds of female. Right, odds ratio of survival for males and females, exp of beta 1. So the way we write this odds ratio for males and females, so that means that you're looking at the odds for males over the odds for females, right? So that's typically the language, right? So it's equal to exp of beta 1. So right, just be very aware of your coding of your indicator variables. So what kind of hypothesis tests do we have in logistic regression? So a lot of these tests, you can view them and realize that there are some similarities with what you've seen so far with ordinary least squares regression, right? So if you're looking to remove a single, so let's say you have multiple predictors, you're looking to remove just a single predictor, we perform what we call a wall test, which is based on the z distribution. And this is analogous to the t-test in multiple linear regression. So the wall test is a z statistic. It's because it's based on the standard normal distribution. It's basically beta sub j hat minus the null value over the standard error of beta sub j hat, right? So this framework looks very similar to the t-test in multiple linear regression, right? The t-statistic, if you recall, is actually the exact same formula. The only difference is that because in logistic regression we use what we call the method of maximum likelihood, and in linear regression with ordinary least squares we use the method of least squares, right? We're minimizing the sum of squares residual. So the coefficients follow a t-distribution for multiple linear regression, but in logistic regression they follow a z-distribution. Right, so that's removing a single predictor. Now, if you want to see if your model is useful or not, right, so you get your multiple predictors in your model, right, we calculate what we call a delta g-square test statistic. Is given by the null deviance minus the residual deviance of your model, right? So it's just of this specific model. The way to think about these, the null deviance, right, represents it's analogous, right? So it's not exactly, it's analogous to the SS residual of the intercept-only model. Right, while the residual deviance is analogous to the SS residual of our model. So obviously the details are a little bit different, right? But basically we're seeing, right, if there's an improvement in the model fit by adding all your predictors versus the intercept-only model. So you calculate this and you compare this with the chi-square distribution with p minus 1 degrees of freedom, right? Because you're looking to drop p minus 1 terms, right? Because we're keeping the intercept. And this is analogous to the ANOVA F-test in multiple linear regression. If you have nested models and you're looking to drop a subset of terms, then you're looking at the delta g-square test statistic again. But now this time it's a delta g-square test statistic where you're looking at the residual deviance of the reduced model. So this is again analogous to the SS residual of your reduced model minus the residual deviance of your full model, right? And you compare it with a chi-square distribution. The degrees of freedom is just given by the number of terms you're looking to drop. And this is analogous to the partial F-test. So that's the test that we have. There is also this group of tests called goodness of fit tests. So they test whether the framework of your model is fine. So you're basically testing in this framework whether this equation that you're considering is a good way to express the relationship. And let's say we have k of these. So the null hypothesis in all of these goodness of fit tests will say that that equation works, and the alternative will write that log of pi over 1 minus pi is not equal to this equation over there, right? So the alternative is basically saying your model doesn't fit well, right? Because if it's saying that this is not equal to that, that means this doesn't fit the model. So in this case, right, you actually want to fail to reject, right? Failing to reject will say that result in you concluding that, right, you don't have evidence to say that the model doesn't fit well. Now, a few things, there are a few of these different hypotheses, goodness of fit tests that exist. These tests require what we call group data. And these group data are usually found in design experiments. Basically, the idea is you cannot have observations that have a unique combination of predictors. And this is very difficult to implement in observational studies. So what do I mean by this? So let's say we keep things simple. We only have 4 data points and 3 predictors, just to keep things simple. Observation 1, right, x1 equals 4, 6, 9. Observation 2, 4, 6, 9. Observation 3, 2, 2, 8. Observation 4, 2, 2, 8. So if you look at the predictors values, observations 1 and 2 can be grouped together because their values are exactly the same in the predictors. Likewise, observations 3 and 4 can be grouped together. So you must have the existence of such groupings available in your predictor space to be able to apply your goodness of fit test. Right, so this is a requirement, and especially when you have more and more predictors, the number of data points that have all the same combinations will get, it's harder to find that. Right, so you compare this situation with another situation, x1, x2, x3, right? Observation 1, 2, 4, 9. Observation 2, 1, 1, 8. So 3, 8, 1, 8. observation 4, 3, 1, 4, right? These values are all unique, right? You cannot group any of these observations together. So this is called ungrouped data, where each row is an individual and their values do not replicate elsewhere. So if you have a lot of observations that have unique combinations, you can't use any of these tests. So your question might then be, right, so what can we do to assess our model? Right, and the other thing you might consider, well, could we use residuals? Well, residuals are not very helpful because your response is basically binary, right? It's coded as 0 or 1. Because of that, your residuals are typically they will not look like they are random scatter. It's kind of hard to evaluate. So your residuals plot will look like curves and lines and all that. And again, to properly use the residual plots, you require data to be grouped. And again, that doesn't exist in a lot of data that you have. So in the next module 10, we'll talk about what else can we do, right? If these tests don't work, what we just usually end up doing is just evaluate the predictive ability of the model.